So it is with great pleasure that I'm introducing our next speaker. So as with all the speakers, you will be able to find their bio on our Indico page, but I will just highlight some of the few details from Fernanda. So Fernanda, it's been a fusion researcher already for many years. She's been participated in the biggest experiments in fusion, CA Cadarache, JET, and she's now currently working at the UKEA. And her current position now is she's the JET Senior Exploitation Manager from Eurofusion. And most recently, you should have seen Fernanda on TV, as Fernanda was part of the team of 3 scientists that presented, that were in this press conference that presented the results of the new JET DT campaign to the world. So we're really happy that Fernanda is joining us today to give us an insight on the developments of JET and what the opportunities are for students and the challenges that will be handling out to the next generation of fusion researchers. So thank you very much, Fernanda, for taking your time to be here with us.
Okay.
And without further delay, please, floor is yours.
Okay, can you see the slide?
Yes.
Perfect. So the title that I was given is How to Drive a Tokamak, but actually what basically I have prepared is a view of magnetic confinement fusion research from the point of view of tokamak operations. So my role at the moment is exploitation manager for Eurofusion, which means that I'm the link between the scientists in Eurofusion who prepare the experiments and the UKA, which is the operator of the JET machine. My career started very much like Elena this morning. I started in doing transport. My thesis is on transport and heat balance. Then I moved to JET, and then I never left. And actually, at some point, I moved to do radio frequency modeling, and my office was, I think, around the corner from Elena. So, a couple of disclaimers. This is a presentation that has evolved from a lecture I gave at the Calum Plasma Summer School, which is targeted at master, PhD, that sort of level. That lecture is an hour and a half, so I had to shrink it. The aim here is really to give an overview of the various aspects, the various bits and pieces, if you want, that are involved in designing and implementing plasma scenarios to carry out experiments in tokamaks. And what I would like to show, I think what I hope to show at the end, is the extent of the integration of physics and engineering knowledge that is needed to run such experiments. I'm very happy that most of the speakers this morning have introduced the concept that I will need. So you will see me repeating some of the concepts, but by now you're all aware of them. And the final disclaimer is that the plots have been taken from published paper. The ones on JET data, please do not reuse without permission. This is Eurofusion. So, very quick reminder of what we need. For the reactor to ignite, to self-sustain, we need enough fuel heated to high temperature and for long enough. And this is the minimum requirement for the triple product, which has the density of the reacting ions, the energy confinement time, so how well the plasma is insulated, and the ion temperature, so how well we can heat the plasma. And I will concentrate on when we sort of spin off into reactor or on ITER, I will concentrate on deuterium-tritium fusion, so alpha particles and 14 MeV neutrons as products. So I will not touch on other types of fusion. So what do we mean by tokamak operations? Tokamak operations is the set, the ensemble of the activities and the processes that go into realizing a tokamak pulse. This is an example from JET. The time is in second. The typical time for a JET pulse is around 20-25 seconds, of which the high power, the really hot phase is about 5 to 10 seconds at most. But you need to go, in order to get to the flat top, in order to get to the heating, which is really the part that it's important for the experiment, you need to go through plasma initiation, so breakdown from an empty vessel, ramp to the conditions, and ramp down and plasma termination. And as Alberto mentioned this morning, the ramp to the experiment and the ramp down are also important. So we'll discuss that a little bit. Now, a tokamak operations also covers pulses that don't have a plasma, but that exercise some of the subsystems. And this is, for example, what will be needed for the integrated commissioning of ITER or of the new tokamaks that are coming online, or even the new stellarators, by the way. So where you have each subsystem first by itself, and then you start integrating and putting them together. So I will talk, as I said, I'll talk about tokamak operations, and then I will go into fueling, heating, and heat transport, so the components of the N-tau-T. And then I will mention heat exhaust, something off normal event and disruptions. Again, Alberto has already mentioned the importance of disruptions. And through the talk, I will talk about real-time control, because that is something that is really, really important in research at the moment. You've seen this. So colloidal field, transformer, primary toroidal field coils, the fact that we induce a plasma current and that you have a toroidal magnetic field. And I will only really discuss the operation of tokamaks, which is a very specific type of the magnetic confinement devices. And I will not go at all into the background of why we do tokamaks and how a tokamak is built. I will just get that for granted. And again, you've seen Alberto describing how this amazing new tokamak has been built. The tokamaks come in all flavors and all sizes. So there isn't a single description, a single way of having a tokamak. And they go from very, very small machines, so tabletop devices, to medium and large size devices, and then to the reactor size tokamak, like ITER and beyond to demo. So here you have a scale of what we call the large aspect ratio tokamaks, going from something fairly small like Compass, ASDEX upgrade at IPV in Germany, JET and ITER. But also sort of over the last 20 years or so, or even a bit more, 20, 30 years, we've gone into exploring more and more what are called small aspect ratio tokamak or spherical tokamaks. If you hear the sort of on the news and when they talk about fusion, the large aspect ratio tokamak is the one they talk about as the donut, and the small aspect ratio tokamak is more like an apple with the core taken out, because it really looks spherical. And this is an example. This is MAST upgrade, the device at Calum. As you can see, it's really shrunk towards the inside. We use the different sizes and the different types of tokamaks to explore different physics and engineering as well. So again, we use data from small and large tokamaks to be able to predict and extrapolate the condition, the physics to what is going to happen in, for example, in ITER. As size varies, the pulse duration varies as well. So a typical tokamak pulse duration can go from few milliseconds from very, very small devices. You've seen from Tokamak Energy, their small tokamak has got hundreds of milliseconds or 1 second, tens of seconds, if, for example, in a machine like JET, where the pulse is limited by the cooling of we run a copper magnetic field coils, so that is the main limiting factor. Few minutes in the superconducting tokamaks that we have around the world. They're called West, East, and K-star. And then sort of 15 minutes and more on ITER, and then eventually a reactor could be steady state. But this is the pulse duration. You need to consider when you look at the tokamak, you need to consider the typical timescales. So although the pulse duration goes from seconds to minutes, for example, the plasma interaction with the wall can go from milliseconds for bursting events or very, very fast events to tens of seconds for the equilibration, the thermal equilibration of the first wall of the tokamak. You have heat and particle confinement times. The characteristic times can go from milliseconds to seconds and typically go up with size. And then you have the time scales involved in the real-time control. And they can go from microseconds to milliseconds to seconds, depending on what you control. So knowing what the time scales are is important because that feeds into your control system, for example. So not just on the operation, but really on the control system that is at the core of your tokamak. The present superconducting tokamaks are beginning to achieve pulse duration in hot conditions, because you need both. You need a long pulse, but you need a long pulse with a very hot plasma. There's no point in having a long pulse in a very, very cold plasma. So this is an example from EAST in March 2022, where they got sort of 1,000 seconds with temperature of the order of 6 kV. So it's really going quite far. These are long pulses. The route to continuous operation in a reactor is still very, very long and challenging. And I have one slide at the end for the current drive. This is a bit more of a curiosity. In the 1990s, JET explored the possibility of doing AC operations. So you have a pulse where the plasma current changes sign. So you have a first pulse with the plasma current in one direction, and then you kind of recharge the primary, and you have a second part of the pulse with the plasma current in the second direction. So you can see the solenoid current going up and down. This is not ideal. There are all sorts of issues as to why a reactor may not be able to do that. But again, curiosity and the fact that already, in the late 80s, early 90s, people were beginning to think about the concept of how can we make this longer? How can we make this towards steady state? So we have some analog real-time systems, but we also have some fairly advanced real-time digital systems. And we use them to control the confining magnetic fields and the plasma currents. These are done because all these circuits, as you can imagine, all these circuits are sort of interacting with each other and with the plasma itself. So we have decoupling multiple input, multiple output systems. We use the real-time control to achieve the right conditions for a specific experiment. So to guide the plasma towards, to optimize the plasma once we are in the high performance phase, in the really hot phase, but also to protect the machine from damage. Protecting the machine in real time from damage is essential, and it's built in any tokamak that you will see. The magnetic fields, so the combination of the magnetic fields that you have around on the machine and the plasma current itself will give you what is called a plasma configuration or an equilibrium. And shaping the plasma magnetic configuration is essential to explore different physics. So these are two examples from JET. This is a discharge where at the beginning, the plasma is in the blue. So this is a poloidal cross-section. And so you see that the plasma is kind of round and squashed towards one part of the inside of the vessel. In the other case, in the red, you can see that the interaction, the light, which is a sign of the main interaction of the plasma with the wall, has gone from this part, so from the limiters, from the main chamber, if you want, to the bottom of the machine. And this is the diverter. And this is achieved by having a single null. So this is what is called a single null lower X point. And this is a null, this point here where the last closed flux surface crosses it, it's a zero, it's a null of the colloidal field. And when you do this, the plasma has some significantly different behaviors than when you have a limiter plasma like in the blue. So this is what you can do to explore different physics. On a spherical tokamak, you can do the same, and this is a masked upgrade. And on masked upgrade, you can do that on tokamaks as well. But on masked it's easier to see because also we've got some very nice images. You can do a double null equilibrium, so where you have a null both at the bottom and at the top of the machine, and that is used for studies of the heat exhaust, for example. And because masked upgrade has got some absolutely wonderful diagnostics, you can really see it in the video images. So if we start from the beginning, we have to produce the plasma. The vessel is empty. You need to have the conditions where the gas that you inject becomes a plasma. And a plasma is something which is fully ionized and dominated by Coulomb collisions. So the aim of the breakdown is produce a sustained ionization avalanche that will lead to plasma conditions that are dominated by Coulomb collisions. So in order to do that, you use the central solenoid to give you an electric field for a given gas pressure that you inject. So you inject a little bit of gas, you start the electric field, and then you need, again, this colloidal field null, which is what I'm showing here. So you can see that this is the magnetic configuration just before the plasma starts. So you see it's very different from the one that I've shown you before. And this gives time to the particles that are ionized to go around and ionize other particles before they're lost to the walls. The one thing that is happening is that we are using, as we mentioned before, we're using the experiments that we're doing now on several machines and the modeling capability to explore what the conditions will be like, for example, for ITER, so that we are ready for an efficient start of the plasma operations and we can tackle the problems foreseen for the breakdown. We know what certain problems could be on ITER for breakdown. We know that it could be more difficult than, for example, on JET, but we are doing modeling, so we're preparing. Often, I don't know how many of you are interested in modeling, but quite often, some of the modeling studies tend to focus on the flat top phase, on the hot phase, on the really high performance phase of a tokamak pulse. But the time leading up to this phase is very important because the evolution of the plasma will determine the static conditions, what are called the target conditions. What I have here are two pulses from JET where the plasma current on the flat top, so towards about 46 seconds, 46 and a half when you put the heat in, the plasma current is essentially the same, and some of the other conditions are essentially the same. But the evolution until then has been completely different. And so, for example, you can see that this is the internal inductance, which is a parameter that tells you how the current is distributed, how the plasma current is distributed inside the plasma itself. And it says that the plasma current is distributed in a different way. So this region, the early plasma phase and the ramp up, it's very important to determine then what you can do. In a reactor, the plasma, the early plasma phase, even if it's very short compared to the burn phase, because the reactor is going to go for longer, it could be crucial because it's a phase where you could have transient heat loss. The entry, sort of this transition from the phase where you heat the plasma from the outside to the phase where you have this burning plasma, which is dominated by alpha particles, could be very delicate. And also this is where in a reactor, you will need the power from the grid because you will be producing not as much power from the reactor itself. So this is a phase again that we need to take care of in the modeling. And again, in the modeling and of course in the experiments. So let's go through the fueling, heating, and heat transport. For the triple product, we need to have sufficient reacting material. So sufficient hydrogenic plasma ions, not just any ion. It has to be the deuterium and the tritium for us. We know that the confinement time, the time of permanence of the ions in the plasma is finite. So we need to keep fueling. The most common method to fuel in present plasmas is injection of neutral gas, either as an actuator for the density control or pre-programmed. This is an example from JET, where you can see that at the beginning, until about 47 seconds, you have a requested density and you have the gas that is controlled by feedback. And then then the density evolves by itself and the gas is essentially constant. So this is pre-programmed. One thing that we need to note and to remember is that the vessel itself, the first wall, also retains and releases gas. So we need to keep in mind the recycling, and that depends on the first wall materials. Carbon is worse than metal. In addition to the fuel for fusion, we can also inject other species. So here you see we're injecting neon, and you've heard this morning already from Alberto that ITER is also considering injecting neon for other purposes, not just for fueling. Fueling with the neutral gas is quite inefficient. We know that about 10–20% of the injected gas actually ends up in the hot confined plasma. So alternatively, people have developed methods to shoot frozen pellets into the plasma. These are really hydrogenic pellets. These are ice, little pellets of ice. You can have them slightly larger. They do more fueling, or you can have them smaller. And of course, the larger ones will penetrate further into the plasma, so they will fuel. The smaller one tends to be at the edge. So we use them for the control of the edge instabilities. And this is an example from JET where you don't see a lot while you have the very high power, but when the power decreases, you can see that every pellet is seen on the density. Now, while in present tokamaks, we operate mainly with gas as our main injection method, pellets are likely to be the main fueling method in ITER and maybe in a reactor. So as you can see, the way we operate will be different in ITER already. Heating is the second aspect of the NTAU-T. Ohmic, let's forget about it. At the temperature of present tokamaks is very small and is negligible in a future reactor. The other methods that you have are neutral beam injection, which is the dominant source of additional heating in most present tokamaks, and it hits mainly the ions. It will hit the electrons in ITER, or wave resonance heating. So you inject radio waves, microwaves, and they corresponding to a particular resonance for the plasma particles, and they transfer the energy to these particles. So examples of these ones are called ion cyclotron resonance heating or electron cyclotron resonance heating, and they use the cyclotron resonances on the magnetic fields. Different heating methods give you different physics. So this is an example. It's a fairly old example from JET, but it's also it's one of the clearest ones. So the resonance wave heating will give you more spatially localized heating effects. So it will really deposit the power at the resonance, while the beams deposit the power more across the radius of the plasma. Both beams and NBI, beams and RF can be changed, can be adapted to give heat to the plasma ions or to the electrons, or both. The beams can make the plasma spin, for example. If you turn the beams in a particular direction with respect to the plasma current, it can make the plasma spin, and spinning the plasma, so the rotation of the plasma has an impact on how good the thermal confinement on the plasma is. As you can see here, ICRH has got much higher electron temperature in this case. The beams have got a very high neutron rate, so while RF doesn't produce many neutrons in DD. Eventually, what matters for fusion is the temperature and the energy of the ions. So whatever you do in terms of heating, the ions are the ones that need to be hotter. In a DT plasma, the 3.5 MeVs produce a fifth of the total fusion power and will heat the plasma. They will do electron heating. So already on ITER, this is a slightly different one than what Alberto showed. He's an insider, so he has much better access to the simulations. But already on ITER, the alpha power will be about, at the highest performance, will be about 100 megawatts, which is more than the external and the additional heating power. So this is a major paradigm change, because we are going to conditions where really there is a degree of self-organization that we don't observe in the plasmas at the moment. So the two things to note is that first, most present tokamaks have dominant ion heating. So the methods heat particularly the ions rather than electrons. Reactors will have dominant electron heating with high energy alpha particles. So the physics will be slightly different. But also this really complex behavior, self-organized behavior, has not been explored yet. So we have to be very careful when we talk about extrapolation of results from present tokamaks to reactors. We do have data. We do have data with dominant electron heatings, for example, and we have data from JET that explore a little bit of alpha power, but we really need to rely on the extrapolations to see what ITER will do. Small parenthesis on the non-inductive current drive. So inductive current drive is the one driven by the central solenoid, by the primary. But there are other methods that can drive current inside the tokamak. One is using external means. For example, the beams can on present tokamaks drive some current. Electron cyclotron heating can drive current, but also internal. There is a bit of physics that tells you that the self-organization of the plasma itself will drive something called neoclassical bootstrap current, and that could be quite a large fraction of the plasma current in certain reactor designs. So this is an example. Note again, this is a 1990. So again, this is nothing particularly new. People have been thinking about it for a long time. This is a more example of a fully non-inductive reactor scenario. Because this is one of the things that, for example, the spherical tokamaks that have this very thin primary or this very thin central solenoid are going more towards something that has significant component of non-inductive current drive. Okay, now let's get back to the third point of the N-tau-T, which is the confinement. So we said before that the plasma is a little bit like a house. You heat it, but if you leak, for example, if your windows leak too much energy, too much towards the outside, your plasma, your house will remain cold. Same thing for a plasma. We have defined this parameter, which is the confinement time, and is a ratio of the measured energy and the power that you're putting in. In normal conditions, there is a diminishing gain for the power increase, because we know that the confinement time decreases when the power increases. Now, this doesn't mean, I know that people say, oh, that the plasma gets colder. No, it means that it takes more and more power to increase the energy when you increase the power. So, however, and this is taken from the original paper by Wagner in 1982. In certain conditions, the plasma enters this improved confinement regime, the H mode. And you can see that in these conditions, the confinement time goes from sort of about 20 to well beyond 40 milliseconds. And this is the H type. So there is a factor 2. The H mode confinement time doubles. The plasma is hotter and there is more fusion for the same heating power. So this is really a major effect. What happens inside the plasma, if you look at the column and if you look at the profile, you see that this edge transport barrier develops. So this is why the heating doesn't go out, because you have this kind of barrier, and it's as if the plasma was put on top of a pedestal. What this edge transport barrier does, and the fact that it's not stable, we'll see it in a second. But in order to enter H mode, there is a threshold in the input power. And this power is commonly described by a scaling law, which has a very strong dependence on machine side, density, and toroidal field. So the bigger the machine, the more power you need to get into H mode. The higher the density, the more power you need to get into H mode, and the same thing with the toroidal field. However, we know that this L2H threshold has some fairly subtle dependencies. So for example, one is the fact that the density is non-monotonic. Dependence on the density is non-monotonic, so there is a minimum. So one of the things that ITER may want to do is to enter the H mode towards the minimum of the density. It depends on the species of the ions, so on the actual composition of your plasma. A hydrogen plasma will have a very high. It goes like the inverse of the mass, roughly. So a hydrogen plasma has a very high L2H threshold for the same density, same conditions. And fortunately for us, deuterium, tritium, and deuterium-tritium plasmas have a much lower threshold, which is very, very nice. It depends probably on the type of heating, and it depends on the equilibrium. So remember what I told you, the difference between a limiter and an X-point plasma. On an X-point plasma, it's very easy to go into H mode. On a limiter plasma is very, very difficult. So all these things, all this knowledge about what the L2H threshold does and how you enter an H mode has to be taken into account when you design an H mode experiment or in the extrapolations to future devices. The caveat here is that most present tokamaks operate in H mode, and there are different flavors of H mode, and there is a whole variety, a zoology of H mode. ITER will be in H mode. Maybe the reactor will not be in H mode. Maybe the reactor will be big enough that doesn't need the H mode. So this is still, and there is a whole category of designs that don't have H mode. The pedestal is very nice. It gives us this very nice heating and confinement. But however, this edge transport barrier develops until it reaches a limit. And at this limit, you trigger what are called edge localized modes. At the end, the insulation at the edge collapses. Particles and heat are released to the wall. So there is a possible damage to the wall. So you see here, these are really filaments that you see at the en masse. But also the plasma energy decreases because all of a sudden your plasma falls down from the pedestal. And you can see I've zoomed in on the at the end that both the density and the temperature and the electron temperature of the plasma collapse. So the EMs are a repetitive burst event in time, and the lower the frequency, the more serious they are. So hence, because the best performance we obtain in the normal tokamaks is what we obtain with the largest elms, we want to control and mitigate these elms. And we need to control and mitigate them without losing the confinement and the performance. We need to control the edge. We need to keep the edge from elming too much, but keep the core hot. And this is where I make a little difference that maybe it's maybe is not fully acceptable, but when I talk about control, I talk about pacing and about synchronizing the frequency of the elms so that we typically increase it. And we know that increasing the frequency of the elms will decrease the size and the impact on the core. And this is what we use the little pellets that I mentioned before. So the pacing pellets will be used on as well on ITER to pace the elms. Or you can mitigate. So you can decrease the effect of the relaxation on both inside the plasma, on the pedestal, and on the wall. And these are a set of different ways. ITER will use resonant magnetic perturbation to essentially to induce some sort of chaotic behavior at the edge, to ergodize part of the edge, or we'll see impurity seeding, and this will reduce the elm activity to a minimum, or even suppress elm completely. Some of you will see in the next few years that the interest in what are called alternative H modes is increasing, and that because they have good confinement without elms. All these things that I've mentioned, we don't pre-program them. So we use real-time feedback control of the kinetic parameters to essentially to control mainly our high power. And for example, what I'm showing here is a feedback control of the plasma energy using the beam power as actuator, while at the same time we control the elm frequency. In this case is with gas, but can be done with pellets. So all the ingredients have to come together, and they have to be managed by a real-time physics controller. You put in all this power, and all the input power will eventually, as we said, because the confinement times are finite and the plasma itself radiates as well, so it will be lost towards the first wall of the vessel. Conduction, convection, radiation. Conduction and convection in an X point, in a plasma with the X point, go mostly down in the diverter. Radiation goes everywhere. So this could have, the impact of this could be either the fact that non-hydrogenic impurities, essentially the components of the metals of the wall come into the plasma, overheating of the wall components. So this is an example from JET where we look at the infrared view of the inside, and we know that the diverter is reaching about 1000 degrees C. It's not a big problem because it's tungsten, but it could be physical all the way to physical damage. If this was beryllium at 1000 degrees C, it would melt. And for a reactor, this could lead to downtime. So, which would be when you're producing electricity with it, it's important. So the management and the control of the heat and particle fluxes has to be an integral time of the scenario development, and it's one of the main constraints to plasma operation. So essentially, it's not that you can do what you want. So the choice for ITER, I'm only talking about this impurity seeding. The choice for ITER is to inject light Z impurities to radiate the power just outside the confined plasma, and it has to be compatible with the core of the plasma remaining very, very hot. This is an example from JET where the red pulse is a pulse where we injected neon. So you can see that the radiation is much higher. The stored energy is higher, So the plasma confinement is good, remains good. And if you look at the temperature of the diverter, as I've shown you in the other slide, without neon, we get up to 800 degrees, and with neon is nicely controlled. So this is the kind of thing that you need to use. The alternative is to design a tokamak with a different diverter. And so you can have the single null, or you can do things like snowflakes, which is also very popular, or you can do something that is called a Super X, which is typically for the spherical tokamaks. And again, the diverter configuration will determine the type and the quality of your H mode. So your H mode, even for the same power, your H mode in a single null will not be the same as your H mode probably on the snowflake. The importance of in a sort of mirror way as the importance of the, yes, I know, I'm looking at the time, don't worry. In the same way that we are worried about bringing the plasma up to high power conditions, terminating safely the plasma is very, very important. And on larger machines, and especially on a reactor, even though this is a very short phase, this will be a main concern. And the concern will be how you exit from H mode, how you exit from the burn phase, so from the phase that is dominated by alpha heating, all the while by maintaining the plasma stable. And this is an example from JET where, for example, one way of terminating the plasma is you keep the plasma in H mode while you're still ramping the plasma current down. And that has certain advantages. So again, these are all the things that we are beginning to incorporate into the scenarios. There are some internal instabilities in the plasma, and there is always something ongoing activity. Most of them are benign and absolutely tolerable. At times, so this is, for example, this is a sawtooth. In normal conditions, this is fine. On a reactor sawtooth, so this collapse of the electron temperature may not be as nice as on a normal plasma. Sometimes even this MHD activity has a significant effect on the plasma. So for example, degradation of the confinement and the decrease of the energy of the fusion power. This is, in this example, you see that at this point, basically the beam power, the ICRF power, the temperature is the same, but the neutron rate is taking a chunk off. So something has happened. The other way where we terminate a plasma in a way that is not normal is when we have to protect the machine. So for example, we look at the health, at the resistivity of the magnetic field coils, at the health of the subsystems, and we need to evaluate the threats to machine integrity. This is done on timescales of milliseconds on JET. And we need to stop the pulse when we detect anything unusual. And we need to stop the pulse safely, because stopping the pulse, the fact that you stop the pulse, the consequences cannot be worse than not stopping. But also the system itself, the real-time protection system has to evaluate based on what it knows about the threats, which is the worst threat, stopping the pulse or not stopping it. So this is a case where, we look at the cameras at the plasma facing components and we see that the temperature in real time is going well beyond the 1000 degrees. So, okay, we stop the heating. The last bit of the off-normal event is the worst of all. It's a disruption. This is a total loss of magnetic and kinetic control of the plasma. It could be physics. The reasons could be physics. So you have one of these large internal plasma instabilities, or it could be engineering. For example, something goes wrong with one of the control coils or control problems. So the consequences are the strong electromagnetic forces on vessel. You have all these currents changing rapidly, and the heat loads on the plasma facing wall. So there is a potential for very serious damage to the vessel. This is an example from JET where there was a disruption and the plasma went up. As you've seen from Alberto this morning, the disrupting plasmas have the tendency of losing control and going up. And we melted the upper part of the vessel, which was beryllium, and it was clear that we melted it. So one of the research topics that is very, very important is the detection of an incoming disruption and the triggering of the mitigation system to reduce the damage. And there are many groups that are involved in designing these systems that predict oncoming disruptions and minimize the potential damage. And this is one of the areas where the exploitation of AI, reinforcement deep machine learning, and where, of course, the increasing available computing power is helping us. This is a 2D, this is a generative topographic mapping applications where we have a 2D representation of a jet disruption probability. So in green is where we don't think a disruption is oncoming, red is where it's probably approaching, and you see the pulse. These are points along in the time evolution of a pulse. Everything was fine, and then it goes in the red. So if you have a real-time control system that does that, which we have, you can stop the pulse at some point. The other application of AI is the use of the operation-oriented modeling and control tools, which can be benchmarked and tested and then refined with reactor data. This is this was the paper in Nature in February, where there was the capability demonstration of magnetic control designed through the reinforcement learning. Of course, because we are talking about a reactor eventually, the reliance on AI will have to be balanced by the nuclear safety aspects. How do we go? I mean, we've learned, it's taken us years to learn to operate today's tokamak. JET is going to be 40 next, from its first pulse was 40 years ago next year. So we have several exciting tokamaks that will start operation in the next few years. And can we use the experience that we've built so far to speed up the path from the machine commissioning to the very high performance active exploitation phase? And the answer to me is yes, because we can exploit the knowledge that we have and the increasing computational capabilities to improve the integrated modeling, including real-time feedback control, exception handling, and digital twins. And I promise I wrote this one before Aaron this morning mentioned the digital twins. And we can distill the experience in operating tokamaks, including deuterium-tritium operation on JET, for example, to extrapolate the processes, not just the physics and the engineering, but the processes that we need to develop to run effectively and safely a burning plasma experiments and eventually a reactor. And we need to focus on training the new generation, your generation, and on development of what is called concept of operations. My final caveat is that what I've said above is relevant for an experimental fusion reactor. Commercial fusion reactor will have one well-rehearsed operational scenarios, and you will not be able to fiddle and do all these experiments, hopefully, but it will need the protection and the real-time control aspects. Those will be needed by a reactor and will need to be even more rigorous because of the nuclear safety issues. And that's all for me. I hope I have given you a feeling of what is involved in driving a tokamak, and you can now appreciate how this is a multidisciplinary field that requires engineering and physics skills. Thank you.
Fernanda, thank you very much. That was a really comprehensive and interesting talk. So I'm really happy that you managed to adapt this presentation from the Colhan Summer School, which, by the way, we also provide financial support for fusion students to go to this school. And yeah, well, thank you very much. This is a really good overview. And and also a challenging presentation, I would say, because you mentioned some of the challenges that are at the moment need to be developed and in JET, and also hoping for the future scientists and to be joining these initiatives. So I would like to open the floor for questions. You can either write them on the chat, as we have been doing it before, or you can also just
Silence.
raise your hand.
Stand silence.
Yeah, no, it's really good, and yeah.
I don't mind silence.
Okay, so we can wait for these questions. In the meantime, I would like to ask you a question, maybe not so related to science itself, but regarding how it's the skills required for a scientist to be able to present results to the general public. Because I mentioned earlier, you were part of the 3 scientists that were able to summarize all the deep research that has been going on JET and be able to transmit it to a general audience, which is not necessarily fully integrated into fusion. So what can you talk briefly about the challenges of this?
I think the first thing is to try to get, I mean, what we presented, it took nearly a month to converge on a presentation, because you need to get very few results. You need to get the main results, and you need to explain them in a very simple way. So you really need to get a couple of pieces of physics or of engineering and put them in context of the more general fusion research. I think it's important to be honest. I think it's important to be clear, not just clear, but also be honest. So don't promise, you know, when people ask you, can we have fusion can we have a fusion in reactor in the next 5 years? Probably not, but we will have, and then you need to answer honestly, but you need to add some upbeat. So you need to make it, don't be too pessimistic. So you can say, no, probably not, but in the next 10 years, we will have a new generation of machines, and that includes some of the ones funded by the public, but also some of the private ones, and they will do more deuterium tritium experiments. So that way, you turn the answers into something that is more positive, rather than a statement that it could be negative, or a statement. And the other thing is that if you're not comfortable with the statement, don't say it. So, for example, if you're not comfortable with promising something, don't say it. Just say, no, I can't answer this, or whatever. Don't try, because they will realize, for example, they will realize that you're not, that either you don't know because it's simply not your field, or that you don't quite agree with the official statement, and hence in that case it's better to be quiet.
Okay, thank you very much. This is really, really important to, especially when talking to the public for the future developments of fusion. So I will move to the next question I saw a hand raised by Cecilio. So Cecilio, if you want to unmute yourself and ask directly the question, you are free to do so.
Yes, thank you very much. Well, before anything, thank you very much for these keynotes. I have a pair of questions. The first one is about the fuel pellets. And I want to know about what's the typical size of these pellets, and what are the, well, which is the mechanics by how they are launched into the plasma, and what considerations have to be made in this process.
So the JET pellets go from sort of little cubes of between 2 and 4 millimeters of hydrogen or of deuterium. There are several ways. You can have a centrifuge, or you can have a little a gun that cuts the sort of, you have a stream of ice the stream of ice is cut, and then there is a propellant. There is a helium. I think he's using helium as a propellant to fire the pellets. Or you can have systems that are based on centrifuge. I can't remember where they have that. And I don't know what ITER. I'm not aware of exactly what ITER is planning for their pellets. But these are the fueling pellets. These are the small ones. The ones that Alberto showed this morning, the ones that look like a sort of the big size, like a cork, like a bottle cork, those are used to mitigate disruptions, and they cannot go into the plasma intact. They are shattered before, so they are deliberately fired against at fairly high speeds against a target, so that they end up in the plasma already shattered.
Okay, thank you very much. And I have a second question. It's about
Cecilio, can we keep your second question for the end of the round, because I have some others, so if you don't mind.
Yeah, it's quick and I think
okay.
It's relevant. But okay, in the configuration and operation of the existing tokamaks, about how many people are involved and what is their general profile, professional orientation?
JET has been run, traditionally has been run with about 500 people. At the moment, we are running with about 250. The profile is extremely varied. It goes from engineering to physics. Engineering, we need all aspects. I'm not just talking about JET. Engineering, we need all aspects from vacuum, tritium handling, power supplies engineering, additional heating, radio frequency, control engineers, software engineers, protection, sort of safety experts. From the physics, it goes from the sort of theoreticians to experimentalists and anything in between. So really, it's very, very varied, and really it's a complex system. And a complex system will need all sorts of profiles. And we get them, I mean, I think the earliest one can be useful in one of those, sort of the earliest we take people is apprenticeship. So the people 18 and 19 that come in to do apprenticeship at JET, and then they become part of the team. So okay. You don't need to be in your 30s.
Thank you very much. I apologize. Thank you.
Thank you for the question, Cecilio. So we move with the next question. So in the chat, Fernanda, there is the question: what is the future for JET's activities and stuff when it will be decommissioned around the end of 2023? And thank you for your presentation.
So JET finishes at the end of 2023. The staff, most of the staff will be redeployed. I think the staff who want, as far as I know, will be redeployed to other projects within the UKA. I don't know what my job will be. I've been told that, don't worry, you will have a job, but I don't know exactly what my job will be. And then the decommissioning, there will be further sort of, we need to keep JET slightly more together for a while, because we need to take materials out for the material studies post-mortem, and then they start the decommissioning. And the decommissioning will take years. So the decommissioning of JET will be an experiment in itself, because it's the first time. It's not the first time that we decommission a DT fusion machine, because there was a machine in the US, TFTR, that was decommissioned. But there the decommissioning was very, very rough. What the UKA wants to do and what UKA is planning to do is a really more advanced way of decommissioning and learning as much as we can. So that's it. That's the end.
Okay, thank you. So for the last question, it would be: what was the most groundbreaking result of the most recent DT campaign of JET, and did the design of ITER change because of it?
Okay, the design of ITER did not change directly because of the campaign, but it was confirmed. The design of ITER changed by the installation of what is called the ITER-like wall, the metal wall at JET. because ITER was planning to start in carbon and then installing a metal wall later on. And the experiments on JET in 2012, 15 demonstrated that no, you don't need to start in carbon. To me, the most groundbreaking result is the fact that we had done a predict first set of modeling, and when we got the results of the DT experiments, they were matching the predictions. So the first result is that we can still do, even if we have this metal wall, we can still do very high performance. So in a sense, it didn't change the design of ITER, but it confirmed that the engineering choices for ITER were solid and were reasonable. And also that our predictive capability has improved so much that the predictions were good. That we knew sort of that they really the result really matched the predictions.
Nice. Well, Fernanda, again, thank you very much for being here. Thank you very much for taking your time for this event. And we wish you the most success on the continuation activities of you in JET. And hopefully we will get some of the students present here to be able to attend your summer schools and your internship opportunities. So
yeah, thank you.
Thank you, Fernanda.